22.2 Charging Objects by Induction. In this section, we will review the outline of our key topics covered regarding electrical charge and material properties. We will begin by discussing the general classification of materials, specifically focusing on the differences between electrical conductors and electrical insulators. Next, we will introduce a third category of materials known as semiconductors. After establishing these material classifications, we will examine the detailed process of charging conductors by induction. Finally, we will look at how charge realignment occurs in insulators when they are exposed to an external charged object. It is convenient to classify materials based on the mobility of their electrons. Electrical conductors are materials where some electrons are free electrons, meaning they are not bound to specific atoms and can move relatively freely through the material. Common examples of conductors include copper, aluminum, and silver. When a conductor is charged, the charge readily distributes itself over the entire surface. Conversely, electrical insulators are materials in which all electrons are firmly bound to their atoms, so they cannot move freely through the material. Examples of insulators include glass, rubber, and dry wood. Because these electrons are fixed in place, when an insulator is charged by rubbing, only the specific rubbed area becomes charged. A third important classification of materials is semiconductors. The electrical properties of semiconductors lie somewhere between those of insulators and conductors. Well-known examples of these materials include silicon and germanium. These materials are incredibly important in modern technology and are commonly used in the fabrication of a wide variety of electronic chips found in computers, cellular telephones, and home theater systems. One of the most useful features of semiconductors is that their electrical properties can be drastically changed over many orders of magnitude, simply by adding controlled amounts of certain atoms to the materials. Let us consider the process of charging an object by induction, starting with a neutral conducting sphere that is insulated from the ground. Within this metallic conductor, electrons move freely, while the lattice of positive ions remains locked in place. Initially, the neutral sphere has equal numbers of positive and negative charges. If we bring a negatively charged rubber rod near the sphere without letting it touch, the free electrons in the sphere experience a repulsive force and migrate to the opposite side. As a result of this migration, the side of the sphere nearest to the rubber rod is left with an effective positive charge, as seen in the second diagram. Continuing the induction process, we now connect a conducting wire from the sphere to the earth, a step known as grounding. The earth acts as a ground, which is a vast reservoir that can freely accept or provide electrons. Because of the strong repulsive force from the nearby negative rod, some electrons leave the grounded sphere and move down through the ground wire into the earth. Next, the ground wire is removed, which leaves the sphere with an excess of induced positive charge that is non-uniformly distributed. Finally, when the rubber rod is completely removed, the remaining electrons redistribute uniformly, leaving a net uniform distribution of positive charge on the sphere. It is important to note that the entire induction process requires no physical contact, unlike charging by conduction. A similar induction effect can occur in insulators, though the underlying mechanism is different. In most neutral molecules, the centers of positive and negative charge perfectly coincide. However, in the presence of a charged object, these charge centers may shift slightly. This realignment produces a layer of charge on the surface of the insulator. The accompanying figure illustrates a negatively charged balloon brought near an insulating wall. The surface of the wall experiences an induced charge separation. Because the positive and negative charges are now in close proximity, this results in an attractive force between the charged object and the neutral insulator. Let us test our understanding with a quick conceptual quiz. Consider a scenario where three objects are brought close to one another, two at a time. When objects A and B are brought together, they attract each other. However, when objects B and C are brought together, they repel each other. Based strictly on this observed behavior, Which of the provided statements is necessarily true? You must evaluate whether the objects possess charges of the same sign, opposite signs, whether one object might simply be neutral, or if additional experiments must be performed to determine concrete information about the charges on the objects. To summarize our key takeaways, we classify materials based on their electron mobility. Electrical conductors possess free electrons, insulators contain tightly bound electrons, and semiconductors have tunable electrical properties. We also learned that charging an object by induction in conductors allows the object to acquire a charge without any physical contact with the inducing body, utilizing a temporary ground connection. Furthermore, while insulators do not possess freely moving electrons, they can undergo charge realignment or polarization when placed near a charged object. This charge realignment creates distinct surface charge layers, which ultimately results in an attractive force. Finally, here are some review questions to further test your understanding of today's material. First, explain how the process of charging an object by induction differs fundamentally from charging it by conduction, such as by rubbing. Second, clearly outline the mechanism by which a charged object can exert an attractive force on a completely neutral electrical insulator. Take some time to review the concepts of electron mobility, grounding, and polarization to ensure you can confidently answer these questions.